the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through vectors, vector arithmetic, and all that fun stuff for the very first time. And yay, we're now talking about linear combinations of vectors. If you don't know what a linear combination is, I gotta tell you, it's probably one of the most important structures within all of linear algebra. We're going to be referencing linear combinations in every single section from this point forward. So it's really important to have a very strong handle of what a linear combination is. This video is going to contain several different topics, so it might be slightly longer than my other videos, but I'll still try to keep it constrained to around a half hour if I can. All right, let's start with a definition here. Given vectors v sub 1 through v sub p all in Rn, so that is they each have n entries and they're all real valued entries, and given p scalars c1 through cp all from the real number system, then the vector y, which is equal to c1 times the vector v1 plus c2 times the vector v2 plus so on and so forth down the line until you get to cp times the vector vp, is called a linear combination of the vectors v1 through v sub p with weights c sub 1 through c sub p. And by the way, you probably notice when I say those subscript notations, sometimes I say c1 through cp and sometimes I say c sub 1 through c sub p. I'm just kind of lazy. I kind of mix it up a little bit. Sorry about that. You'll just have to infer what my intention is. So a really quick example of this. You have these three vectors right here, v sub 1, v sub 2, and v sub 3. I said it properly. And let's create three scalars. Well, the linear combination of those three vectors with these weights is the following vector. And of course, you can compress those down into the single vector just using properties of vector addition. There you go. The vector 2, 5, 3 is a linear combination of the vectors v sub 1, v sub 2, v sub 3. How did I get that vector y, which is 2, 5, 3, from those three vectors? I used the weights -2, 5, and 4. I often think about creating linear combinations to target a vector as those old movies where you saw somebody at a radio and they were trying to dial in some type of frequency and they would turn these dials so that they could target the actual frequency they're trying to listen to. The frequency they're trying to listen to is the vector y, and they would turn this dial right here maybe 2 units in this direction, and they would turn the second dial 5 units, maybe in this direction, and the third dial, they would turn 4 units in this direction. That's kind of how I think about it. You're just turning those dials to a proper frequency so that you can target this correct vector. But the most important thing for now is to note, whenever you have the sum or difference of vectors, and that sum or difference will always have scalar coefficients, whether they're ones or zeros or negative numbers or positive numbers, fractions, decimals, doesn't really matter. That summation is called a linear combination. And those scalars, the coefficient scalars, are called the weights of that linear combination. And as you can read right here in the note, the weights in a linear combination can be any real number, including 0. Now, before we go into a lot of other theory on linear combinations, let's get a visual of them by hopping over to Desmos. All right, so here we are in Desmos, it's a little applet that I kind of wrote up very quickly here. We have two vectors. The red vector, I'll go ahead and call that u, and is the vector 2, 1 right now. And the green vector, we'll call that v, is the vector -1.5, 1. Now, how do you interpret linear combinations geometrically? Well, you could imagine if you want to go forward 2u plus 3v, you would go forward in the direction of u twice. So you'd end up right here, and then you would go over in the v direction, which is this green direction, but along this line, this dashed line, you go 3 steps, 1, 2, and 3. So you'd end up right here. That point right there is going to be 2u plus 3v. That's the linear combination, 2u plus 3v. Now you obviously don't have to keep these vectors u and v like this, so I'll change them around a little bit. Let's make this a little more interesting, something like that. And so if you want to know what negative 2u plus 2v is, let's say, I'll go backwards 2 in the u direction. Remember, u is the red vector, so I'll go backwards 1, 2 steps here, and then I'll go in the v direction 1, 2 steps. So negative 2u plus 2v will get me to negative 2, 3. That's the vector, the resultant vector is what we'd call that, of that linear combination. The whole point here is that no matter what, you can get to any point in this space by using a linear combination of those two vectors. So you might say, wait, how would I get to the point 0, 1 then? How would I get to this point right here? Well, the way you would do that is you go forward in the u direction a fraction of u, maybe like, let's just say 1/4 u, and you'd go in the v direction maybe 1/2 of a step. So you can get to any point in R squared using a linear combination of u and v. This is such a good way to view linear combinations of vectors geometrically. It doesn't work for vectors described by functions, but right now you're probably not dealing with that, so ignore that last sentence. All right, now that that is done, let's go ahead and take an example where we have these 3 vectors, a sub 1, a sub 2, and then the vector b. And we're being asked, determine whether b can be generated or written as a linear combination of the vectors a sub 1 and a sub 2. And then rewrite your work from part A as an augmented matrix of vectors. Well, part A is actually, it totally belongs to the material we're learning right now. Part B is a preview of where we're going to be going in the future. But let's go ahead and deal with part A right now. I just want to know, is there a way to create B as a linear combination of the vectors a sub 1 and a sub 2? That is, does there exist scalars c1 and c2 such that c1 times the vector a sub 1 plus c2 times the vector a sub 2 turns into the vector b? Can we find scalars that will make that happen? Well, if you take a look at this, it's a vector equation. That is, it's an equation full of vectors. That may be the first time you're hearing this in your linear algebra course, but that is actually true. It is a vector equation. Often we really like to write it the other way, where the equals is on the right hand side and there's our linear combination, or the result of our linear combination right there. It doesn't really matter, does it? Anyhow, so let's go ahead and write in what the given vectors are. We have some scalar c sub 1 times the vector a sub 1, which is 1, 2, 3. Then we have the scalar c sub 2 times the vector a sub 2, which is negative 1, 4, 3. And this is supposed to equal, hopefully, some vector b, not some vector actually, the vector negative 7, negative 1, 9. Again, our hope is to determine if that right-hand side vector b can be generated or written as a linear combination of those two vectors a sub 1 and a sub 2. Now, through scalar vector multiplication, we could rewrite this equation as follows. And of course, through vector addition, we can combine those two vectors on the left-hand side so that we have this result right here. And if you take a look at that, if these two vectors are equal, then this entry has to equal negative 7, this blue entry has to equal negative 1, and this green entry has to equal 9. Notice that's 3 equations. And in fact, I'll go ahead and write it that way. Now, before we go ahead and try to solve this, I want to draw your attention to the structure of this system of linear equations. The first column, if you will, has coefficients 1, 2, 3, which is exactly the coefficients of the vector a sub 1. The second column has coefficients -1, 4, 3, which again are the coefficients or the entries in the vector a sub 2. And the right-hand side, -7, -1, 9, is exactly the vector b. So this vector equation that we started with has suddenly become a system of linear equations where the coefficients match up quite well with the vectors we were handed. And in fact, we could write this as an augmented matrix. And you can easily see this is the vector a sub 1, this second column is the vector a sub 2, and the third column is the vector b. We're going to draw our attention to that a little bit more in detail in a few moments, but let's go ahead and use the row reduction process to go ahead and see if there's a solution to this. We get down to this guy, we're going to do one more set of row operations. I'll just take the opposite of row 2 and add it to row 3 here. And notice this augmented matrix. I don't usually write the augmentation bar in there, but let's do it so we really know it is actually an augmented matrix. This augmented matrix has 3 pivot columns. It has a pivot in the first column, the second column, and the rightmost column. And we happen to know from the existence and uniqueness of solutions theorem for linear systems that if your augmented matrix for your linear system has a pivot in its rightmost column, that system is inconsistent. Again, that's because you're essentially saying 0 of those C1s plus 0 of those C2s is equal to 17. And that's a big no-no. That doesn't happen, right? That breaks the world. So we know this system is inconsistent, which means there's no solution to this linear system, which means there's no solution to this vector equation, which means there are no weights C1 and C2 such that C1 times the vector a sub 1 plus C sub 2 times the vector a sub 2 will ever equal b. That is, b cannot be a linear combination of those two vectors a sub 1 and a sub 2. So there you have it. There's no way to get b to be a linear combination of those two vectors. Now, I have actually just demonstrated the process of determining whether you can find weights so that vectors form a linear combination of another vector. And it all boils down to building a matrix and using row reduction to see if there's a solution to the related linear system behind the scenes. Now note in part B here, we're asked to rewrite our work from part A as an augmented matrix of vectors. And we sort of already did it right here. As an augmented matrix, the first column was the vector a sub 1, the second column was the vector a sub 2, and then the augmentation column was the vector b. That notation is very powerful, and we're just about to use it in a theorem. And that theorem is this guy right here. I would call this theorem the Equivalence of Solutions theorem part 2. We already have an Equivalence of Solutions theorem part 1 earlier on in this course. And that theorem basically told us back then that if the augmented matrices of two linear systems were row equivalent, then the two linear systems were equivalent. This one, on the other hand, tells us if we're given a vector equation like we just had, right? We just had a vector equation c sub 1 a sub 1 plus c sub 2 a sub 2 is equal to b. Well, this is just a more general vector equation. So suppose a vector equation's been handed to us. Well, that vector equation has the same solution set as the linear system whose augmented matrix is this augmented matrix right here. The first column is the vector v sub 1, the second column is the vector v sub 2, and so on and so forth down the line until you get to the nth column, which is the vector v sub n, and then the rightmost column, which is the augmentation column, is the right-hand side of this vector equation. It is the vector b. this aligns very nicely with our previous example. This guy right here, we started with building a vector equation and we found out the solution of this vector equation was basically aligned to the solution of the system whose augmented matrix was this guy right here. The first column being the vector a sub 1, the second column being the vector a sub 2, and the rightmost column being the vector b. Now, honestly, I'm not going to prove this theorem. However, the next theorem I actually am going to prove. And here is that theorem. The vector b can be generated by a linear combination of the vectors v sub 1 through v sub p if and only if there is a solution to the vector equation x sub 1 v sub 1 plus x sub 2 v sub 2 all the way through x sub p v sub p is equal to the vector b. Now let me state this again because, well, when written as a theorem, it's a little more convoluted than it needs to be. The point of this theorem is to tell you, if you got a vector b, and then you have a bunch of other vectors, and somebody says, I bet you can dial in these vectors. You can kind of radio dial these vectors in, right? As I mentioned earlier, it's like those old time movies where you have radio operators and they're turning these dials in specific combination to match a frequency. The frequency we want to match is the vector b. These dials are the vectors v sub 1 and v sub 2 and v sub 3. I'm just going to write v's in there for now. And how much we turn them is the weights of the linear combinations that will eventually generate b. So this might be, let's say, -5. We turn it 5 units to the left. This might be 2 units to the right. We're not going to turn that one at all, and so on and so forth. And if that's the case, then turning those dials in that arrangement right there targets the vector b, or builds that vector b. Therefore, b would be a linear combination of those vectors v1 through v6 in this case, with the weights -5, 2, 0, 1, -1, and 2. And again, what this theorem is saying is, if you're hunting down some vector b, well, you know it can be generated by your vectors or by your dials if and only if you can find some way to turn those dials so that the linear combination of those turns times those vectors becomes the target vector b. I know that at the end didn't quite make sense, but that's what it means. Now remember, an if and only if is a bijection, which basically means we're going to have to prove this in both directions, forwards and backwards. We'll start, obviously, by proving it forwards. That is, we're going to say that b can be generated by a linear combination of vectors. Suppose that b can be generated by a linear combination of the vectors v sub 1 through v sub p. Now, where we want to arrive at is that there is a solution to the vector equation x sub 1 v sub 1 all the way through x sub p v sub p equals b. That is, we're trying to arrive at this statement right here. Well, what does it mean that b can be generated by a linear combination of the vectors v1 through vp? Well, that means there has to be some constants, some numbers c1 through cp that are the weights that we can apply to those vectors so that it sums, that linear combination sums to b. And that's what I'm saying here. Then there exists constants c sub 1 through c sub p such that the linear combination of those vectors with those weights c1 through cp should become the vector b. That is, the equation x sub 1 v sub 1 plus x sub 2 v sub 2 all the way through x sub p v sub p is equal to b has a solution actually. It's those weights that we've listed up above, these weights right here. So that actually proves the first part, right? Supposing that b can be generated by a linear combination of the vectors, we arrive at the fact that that equation, x sub 1 v sub 1 all the way to x sub p v sub p equals b, has a solution, because guess what? If b can be generated by a linear combination of those vectors, there has to be scalar weights that we can place upon those vectors that will solve that equation. That's the definition of a linear combination. Now we're going to go ahead and prove the other direction. We're going to suppose there is a solution to this equation right here, and we'll want to arrive at the fact that b can be generated by a linear combination of these vectors. So again, we're going to start with that first bit of highlight, that there's a solution to the vector equation that you see right there. So there we go. If x sub 1 v sub 1 plus so on and so forth to x sub p v sub p equals b has a solution, well, there must be constants that we can plug in for x1 through xp so that those constants are weights on the vectors v1 through vp that generate b. And that's exactly what I'm saying here. There are constants c1 through cp such that c1 v1 plus c2 v2 all the way to cp vp must be the vector b. Because again, we're assuming that this equation has a solution. The solution I'm just going to call c1 through cp. Hence, b is a linear combination of the vectors v sub 1 through v sub p. Thus, b is generated by these vectors, which is exactly what we wanted to say. B can be generated by these vectors right here. So we have arrived at the end of the proof. We proved both directions. QED. Very, very nice, clean, easy proof. Not too terrible. If you didn't get it, if it just didn't work for your brain, please rewatch this. It is actually worthwhile to get used to these proofs. So again, rewind the tape and rewatch it if you can. All right, I think I'm done with this video. I thought I'd keep it short, even though it's not. But I think I did a pretty good job of not keeping it going too long with it. All right, I will see you in the next video, hopefully. I hope these videos help you out, and I hope you have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.